this is part of the review for the final exam, and the first thing I'm going to do is solve this first order differential equation. And the first thing we need to do is decide what type of differential equation it is. And since we noticed that the highest derivative in this differential equation is y prime, and the power on y is the first power, and there are no situations where we're multiplying y's and y primes, then this is going to be a first order linear differential equation. And we can actually put it in the form of a first order linear differential equation. So I'm going to add the 5y to both sides. And I'm going to divide through by the x plus 2. I'm going to solve this differential equation using the integrating factor method, which means that the coefficient of y prime must be 1. So if I divide every term through by x plus 2, I am going to get y prime plus 5 over x plus 2 times y equals 3x over x plus 2. The next step is to find the integrating factor, and that's going to be the integral of the function which is in front of y, e to that integral. So the integrating factor is e to the integral of 5 over x plus 2 dx, and that, if I pull the 5 out, I get e to the 5 times the integral of dx over x plus 2, which ends up being e to the 5 times ln of the absolute value of x plus 2. If I assume that x plus 2 is positive, then I can drop the absolute value here, so I'm going to assume that. And so I'm going to actually end up with e to the ln of x plus 2, and because the 5 can become the exponent on x plus 2 by properties of logs, we get e to the ln of the quantity x plus 2 to the 5th power, which is equal to x plus 2 to the 5th. That's my integrating factor. Next, I'm going to multiply both sides of this differential equation by the integrating factor. So on the left-hand side, I'm going to get x plus 2 to the 5th power times y prime plus x plus 2 to the 5th power times the second term. I'm going to have the cancellation of one of these x plus 2's with the x plus 2 in the denominator. So I get 5 times x plus 2 to the 4th power times y is equal to, and then again I'm going to get a cancellation of one of the x plus 2 factors with the denominator. So I get actually 3x times x plus 2 to the 4th power. Okay, so the next thing I need to notice is that hopefully if I've done my integrating factor correctly, the left-hand side of the differential equation is going to break down to the derivative of the product of the integrating factor and y. So let me go ahead and just write that down, and I'll double check to verify. I'm going to leave my last step down there for just a minute. So the left-hand side should be the derivative with respect to x of the integrating factor, which was x plus 2 to the 5th power times y. And that should equal the right-hand side, which is 3x times x plus 2 to the 4th power. And so on the left-hand side, if I differentiate this product, it's the derivative of the first factor, which is 5 times x plus 2 to the 4th power, and then the derivative of the inner function is just 1. So I get 5 times x plus 2 to the 4th power, which is actually right here, times the second function, which is y. I'm using the product rule, plus the first function, x plus 2 to the 5th power, times the derivative of the second function, which is y prime. So I have checked, I did get the correct integrating factor because it breaks down to this product. Okay, the next thing I need to do, I'm going to erase this, is I'm going to integrate both sides with respect to x. On the left, I just get x plus 2 to the 5th times y, because I'm taking the integral of the derivative with respect to x, both with respect to x. On the right-hand side, there's a little bit of work I have to do, but it's actually going to be simpler if I do a u substitution. So I'm going to let u equal x plus 2 to do this integral. So if I do u is equal to x plus 2, then du is going to actually equal dx That's my substitution. And this is going to be 3 times the integral. Notice that x is actually going to equal u minus 2. So I get u minus 2 times u to the 4th power du. And then on the right-hand side, the integral is the integral of u to the 5th minus 2u to the 4th du. And on the left, I just have x plus 2 to the 5th times y. If I do the integral on the right, I get u to the 6th over 6 minus 2 times u to the 5th over 5 plus a constant. And the left-hand side stays the same. And then I need to substitute x plus 2 back in for u. So I am going to, actually let me simplify by multiplying through by this 3. I get 1/2, and then u to the 6th is x plus 2 to the 6th power. And then 3 times 2 is 6 over 5. And then u to the 5th is x plus 2 to the 5th plus a constant. And then on the left I get the x plus 2 to the 5th times y. Last thing I need to do is to solve for y. So I'm going to divide every term through by x plus 2 to the 5th. And that leaves me with y on the left equals 1/2. If I divide x plus 2 to the 6th by x plus 2 to the 5th, I'm left with x plus 2 minus 6 over 5. This term divided by x plus 2 to the 5th leaves me with just negative 6/5 because the x plus 2 to the 5th in the numerator and denominator cancel. And the last term is c over x plus 2 to the 5th power. So that is the answer. Since there are no initial conditions given, I can't solve for that arbitrary constant. So that's the answer to that solution to that differential equation.